Hello, my name is Z. Today I want to introduce my paper, Data-Driven Abductive Inference of Library Specification. So the problem we want to solve is a verification problem. We try to verify over the client and library program. Here we have a client code and a stack library. The client code is a concat function which can concat two stacks together. And this client code is built from four interfaces of stack library: easy empty, push, top, and tail. The assertion we want to prove is that the head element of output stack should be the head element of first stack. But if first stack is empty, it should be the head element of second stack. We summarize this as assertion: the head element of output is the head element of one of the inputs. And we also want to verify some membership property. The member of output stack could be the member of first stack or the second. So we say the members of the inputs are also the members of output. Now we have the client code, assertions, and the stack library, but the verification is still challenging because the source code of library could be too large to verify, or rely on some complicated data structure, like red-black tree, or be written in a different language. Okay, the common point here is the source code of library could be unavailable, or we say they are black box. Typically, people use specifications to reasoning about the missing implementation. But where do these specifications come from? Most libraries do not provide specifications. So the solution is use data to infer these specifications. Intuitively, we can have a tester which can generate some random inputs, and we execute this black box implementation over these inputs to get some data. And we use this data to infer some specification which can verify the assertions. Okay, before we move on to the details of our method, I will first introduce the workflow of our tool. So our tool called Elrond is a tool for automatically inferring specifications of black box library implementations which enable push-button verification of client programs. So the input of our pipeline is a client code, safety assertion, black box library implementation. And the first problem we are facing is how to approximate the behaviors of multiple library functions. So our solution is use data-driven inference. But the infer specification may be overapproximate, preventing verification of client. And then we use data-driven strengthening to refine it to safe specification. But this specification can still be overfitted, which means that it can disallow some safe behaviors of implementation. So we use data-driven abduction to find some weakness one within all safe specification, and we call this specification maximal. Okay, let's move on to the first procedure, the data-driven inference. The data-driven inference just means we infer specification from the data to prove the assertion. Let's focus on the function top here. The function top takes a stack we call S and return a value, the top elements of the stack we call new. So the specification of stack should also involve S and new. And we try to verify some property of head and the head element and membership. So we summarize this property as the method predicates, head and member, and build some terms in our specification. Like the head as u means element u is a head element of S. And we can also add some quantifier variables here, some for all elements u. We have to mention we actually build a hypothesis base of searching. Here's a trade-off between the expressive power and complexity. We can add arbitrary many method predicates and quantifier variable, but it will make our searching go slow. Okay, so the application of method predicates over variables, we call them features, are orthogonal, and work like a sort of Boolean valued abstract domain. We generalize the concrete data as a Boolean interpretation of these features, we call the feature vectors, and then we learn specification from these feature vectors to build some specification, and these specifications are generalized. Okay, so let's sample the value of u as 0 with the Boolean interpretation of a member as u. Okay, because we know the s is the value of s is 1, 2, value of u is 0, and we just ask is 0 the member of 1, 2? Answer is no. So the interpretation is false. And 0 is not the head of 1, 2. So they will still have false. And 0 is not equal to 1. We have false again. Here, false, false, false is a reasonable generalization of u is equal to 0, s is equal to 1, 2, and nu is equal to 1 within our abstract domain. And we can sample u as 1, get a new feature vector, and another one. From this feature vector, we can learn some specification. For example, we find u is equal to nu if only if u is a head element of S. And we can make the specification. And we can learn specification for tail too. And now we have 4 features. Okay, use this learning mechanism, we can learn the specifications. But are these good specifications? Well, this specification probably be too overapproximated to prove the client assertion. So we have to use a data-driven strengthening. Here is the overapproximation example. We have the client code, assertions, and specification we just learned. And we have SMT solver. We ask the SMT solver to prove the assertion, but the SMT solver returns a counterexample. And this counterexample say, the first property you give me is correct because the output stack is A, the head element of output stack is A, is also the head element of first input stack. But second property failed because the one of the member of output stack we said is also A is not the member of first stack. But it is strange. We know A is the head element of first stack. It should also be the member of first stack because we know they're exactly the same A. But the SMT solver does not understand the inductive structure of this, and it cannot understand the relation between member and head. So, because the member and head are uninterpreted functions, so the SMT solver returns this kind of counterexample. We have to strengthen the specification somehow to rule out this counterexample. For example, we can strengthen the specification of top. Let's recover the feature vectors of top. The idea here is try to treat the counterexample as a data. Here we focus on A. A is not the member of first stack, but A is the head of first stack. So we have a feature vector, false, true, true. Because the situation is something we try to rule out, so we label it as negative. And other feature vector are sampled by some execution, so that's a good feature vector, we label it as a positive. And we can learn a specification as a classifier to separate the positive and negative. For example, we have the specification u is equal to nu if only if the u is both head and member of S. And we can use this specification to rule out this counterexample because this time you have to be both member and head of S, the first stack. Okay, now we refine the specification as safe specification, which can prove the assertions. But are this good specification again? Well, this specification to be overfitted with to be consistent with the black box library implementation. So we have to use data-driven abduction. Here is the overfitting example. Previously, we are lucky, which means that we learned some correct specification. But if we have some incomplete testing, which means we lose the situation u is equal to 1, and we don't have the feature vector true to true here. And we will learn some overfitted result. Here we say no elements is a head element of the S. That is obviously unreasonable, but it can still rule out the false feature vector, the counterexample. So it's still a safe specification. Intuitively, a safe but overfitted specification means that it can apply the assertions. But we want to find some maximum specification, which means this maximum specification is weaker than it. There is additional part disjoint with the overfitted specification, and they are not overlapped, but can still imply the assertion. So left-hand side is weaker, right-hand side is safe. So the additional part can imply the negation of overfitted specification and assertion, and the additional part is not false. So it is an abduction problem. But how to do abduction over specification involving inductive data types? Okay, our solution is use data again. So what is this abduction additional part? Here is that they are exactly the feature vector we're missing during the sampling. The feature vector true, true, true. The maximum specification label is lit as positive, but overfitted specification label it as negative. If we can find this feature vector, we can use this to refine the overfitted specification to the maximum one. So how to find it? Okay, we can ask a question. Is there a negative feature vector can be turned into positive but still keep the safety and encoded as a SMT query to ask the SMT solver? The SMT solver say yes, okay, we find this feature vector and we label it to positive, use that to refine the current specification to weaken it. And we do abduction over the weakened specification again, ask the same questions. This time the SMT solver probably say no, and now we know the current specification is the maximum one. Okay, let's move on to the evaluation part. We evaluate Elrond on 27 benchmarks, which include rich data types and complicated properties. And we can learn non-trivial specification. They're very complicated to let the people write it down manually. On these 27 benchmarks, we do data-driven inference and strengthening. And we can find all benchmarks has wrong assertion, and the inference strengthening can be done within 3 minutes. For the rest 22 safe clients, we do data-driven abduction with 1 hour time bound. We can finish in 87% of benchmarks, others are timeout. And all the specifications we infer are correct. We verify them manually in Coq. So why we have a 1 hour time bound? Because during the data-driven abduction, we find the SMT solver spend more time when the current specification is close to the weakest one. So we have a figure here. The x-axis is number of weakening iterations. The exponential y-axis is the query time in seconds. So we find the cost of abduction gets higher, which means a higher time bound will have a few benefits. Okay, here's our conclusion. The problem we want to solve is to infer specification for black box library implementation to enable verification involve rich data types. And our method is use data. And our pipeline takes the client code safety assertion and black box library implementation as the inputs, solves 3 key challenges. The first is infer multiple specifications for black box library implementation. Our solutions use data-driven inference. The second challenge is to overcome the overapproximation. So our solution is to use data-driven strengthening. The third challenge is overcome the overfitting. Our solution is use data-driven abduction. So our artifacts is published in the Zanado. Here's a link in the bottom of the slides. And our artifacts are reusable, functional, and available. Thank you.